We're going to try something a little bit different this time. I want to take an opportunity to actually go through and just lecture a little bit over the content of the textbook because what they've got in here is a pretty good representation of how this works. So we'll take a little quick tour through the textbook here. I'm going to start out talking about the difference between a WAN and a LAN. The LAN is the local area network, whereas a WAN is a wide area network. So your network at home or in a small business or even inside of a corporation, those would be considered local area networks. And the thing about the local area network is because it's based on an Ethernet technology, the bandwidth, the transmit capability and receive capability within that LAN is actually uh, very large. We have a gigabit local area network, which means there's a lot of traffic that can go back and forth over the LAN. WANs, on the other side of the fence, are those communications that occur outside of the local area network, between the office building and the internet, or a remote office and a corporate office, those that are geographically separated. And a big distinction there is that wide area networks are much slower in terms of transmit speed and many connections that make up the internet. So those types of transmission technologies are completely different than an Ethernet LAN. Typically, with a wide area network, we're talking about things like frame relay or asynchronous transfer method ATM, cell technology, or different types of high-speed things. Whereas on the local area network, we're basically working with strictly the 802 series of Ethernet specifications. Now, the original drawing down here of the Ethernet that Robert Metcalf did is actually quite accurate. I actually put something like that together back in the day. The original Ethernet was done over a big, thick coax, and it was called an Ethernet coax cable, and you did put terminators on either end, and you had to put these taps, these vampire taps, into the cable. Every so often, there was a specific distance apart that they had to be. The whole thing was only 100 and some feet long, and so you were actually quite limited in the number of computers that you could hook up to one LAN segment. So this is a good example of that. Now the author also talks about something he calls the party analogy of how Ethernet works. And his description is pretty accurate. I have a tendency to use a different description, that of the hallway analogy. If you're in a school building or an office building that has a long hallway with a lot of doors off of it to different rooms, it's similar to where each room might represent a computer. And when anybody needs to send information to somebody else on the local area network, they just open the door to the hallway and shout the information down the hallway, and whoever's, well, usually the doors are all open, whoever's listening listens, and if it's the information is for them, then they accept it and they take it. And so that's what you call a broadcast environment. You just kind of stick your head out in the hall and broadcast to the entire hallway. So that's one other way of looking at it. So that's what the Ethernet protocol is. He talks about the start and stop and pause, and it's an amazing thing to think about all the network traffic that's going on the area, on a local area network at any given time. There really isn't much time that things are not uh, being broadcast. So there's not much in the way of quiet time. So people just, I mean, essentially the information just gets broadcast out there, and if there's any collisions, then it's up to the Ethernet hardware, the switches or the hubs, to take care of those collisions and ask for repeats. He does mention here about connecting your computer to the internet, and this is something that's a good thing to understand, help you with specking out different types of connections and how you might want to do things. When you connect your home or small office to an internet service provider, they provide that connection to you. So the ISP would bring in a circuit to your facility, whether that's a DSL circuit, or a cable TV coaxial circuit or a wireless circuit. Some circuit will come into your house. And as this diagram illustrates, same thing happens with coffee shops. You have some kind of a modem typically that will take the IP information from your local area network, convert it into frequency or signal carrier technology, depending on what type it is that the internet service provider is using, and send that to their network equipment. From there, it goes out through their internet gateway, which would typically be to one of your large service providers like Verizon or Sprint or AT&T, someone of that magnitude, which channels it into the internet. And on the other end, you just kind of reverse the process. The example down here perhaps is the University of Montana, where they have a internet gateway and they have a circuit, a high-speed circuit, because they have so many users that go into their internet server and connect up to the LAN and service all the different users and hosts and resources like the Moodle that we use. So that's how your house gets connected over the internet. There's another little term in here called the intranet. The term intranet differs from the internet in the same way that we talk about intrastate communications or interstate. When you're traveling outside of the state or outside of your local area network, that's internet. And if you're staying within your local area network or the state, that would be intrastate. Wireless networks have recently become very prolific. We're seeing more and more people connecting to the internet over a wireless network. The thing you want to remember here is the protocol. The 802 series is the Ethernet protocol, and the 802.11 is the wireless protocol. Typically, I think it's 802.3. That's the wire-based. This is where we use radio frequency signals to transmit the IP packets over the internet. Here's an example of a Wi-Fi network config where the router is connecting various desktop computers, smartphones, sending that traffic to the modem, which again goes out on the internet. The dynamic host protocol, the DHCP, is something that is used a lot these days, particularly in small environments such as the one in the picture there. In that picture, the router would be responsible for handing out IP addresses. Since they're just temporary, as people move in and out of a coffee shop, for instance, the router hands out an IP address. And then when that person leaves, they know they're gone, and then they can hand it out to the next person that comes through. This is opposed to static IP, which is where you, as a system administrator, would configure each specific device with what IP address that it would have. So the next big section that we're going to talk about here is the DNS system and how domains work. But we've already gone through and talked about the TCP/IP addressing scheme and how that is all done with the 4 octets, as in the example here of 128.208.3.136 being the address for a specific computer. That computer has a host name of SPIF, and that computer SPIF resides on a domain called cs.washington.edu. So the domain naming system is an organizational method of keeping things within the whole internet system organized and allowing people to have control over certain parts of that. So the very top level domain is what we would call, well, there's the very top, which are the root servers, and below that is what we call the primary domain, which in this case, we're showing the edu. So the breakdown is that the The furthest right of the domain name, the .edu, is the primary or top level domain name. In the beginning, there were only 7 of those. Those were like edu, .mil for military, .com for commercial, .gov for government, .net, and there was a couple of other ones. Those have since expanded. There are quite a few more of those these days. So here's a nice graphic that shows kind of how this works. So within the edu domain, the educational domain, you can have different schools that reside in here. For instance, University of Montana would fit in here, or the Washington school that he's talking about. Further subdomains within Washington would break down here to be the astronomy department and the computer science department. And below the computer science department are a couple of specific computers. So that's why we have here the cs.washington.edu as an example of one specific domain. So the Washington University then controls that domain. Here he talks about the top level domains that I just mentioned, and goes on to add some additional information that because the internet was invented in the United States, they had to do something to accommodate the rest of the world. So the normal top level domains, the com, the edu, gov, and so on, those were for US organizations. What they did was take the mnemonics 2-letter extension and add that to the domain for the rest of the world. And they have here the whole chart, so you can figure out which things are which. Good examples are UK for the United Kingdom, RU for Russia, CA for Canada, and so on. Okay. So how do the DNS servers work in reality? Each computer is assigned a DNS server, whether that information is assigned statically or through the DHCP information that's handed out. Each one is given a DNS server to do the name to IP address translation. Typically, in a small environment like your home, that initial DNS server is just your router. Of course, your router really only knows about a couple of things, and those are the things that are in your house. So if you try and go out to something like on Google, google.com, your router does not know how to get to that. Therefore, it will go and query the next DNS server that's further up the chain from it. This then continues to go up until the DNS server finds one that is an authoritative name server that can provide the address that you're looking for. The example here that the author uses is air and space, some specific computer.si.edu. And he shows here at in the Windows 7 operating system how the DNS server is configured. So you typically have 2, a primary and a secondary. That's because the internet likes to have redundancy. They're preferable to have more than one server handling the load in case something happens. You don't want the internet to go down. At the very top level, there are 13 root servers. Those are scattered throughout the world, and those are the most authoritative name servers that there are. There are also a lot of what we call mirror servers that mirror those 13 root servers, such that that information and processing can be spread around, but they are identical to the ones that they're mirroring. Let's talk briefly about the concept of caching. This is used not only in DNS, but it's also used in other computing environments, and like on your microprocessor, your CPU has a cache mechanism. And the idea is simply that information that's been requested isn't immediately thrown away. It's kept for just a little bit in a special area called a cache in case that information is needed again. This makes sense in the DNS world because if you go and browse to a website, your computer is going to be constantly requesting address translation. And so if the DNS server keeps that information locally in its cache, it can respond a lot faster, and it does not have to go out to the higher up name servers and get the information all over again each time your browser refreshes or you go to a different page on the same site. It is an amazing system, as he mentions. It's completely decentralized. Technically, nobody's in charge. The IANA really takes care of the root servers. Here's a nice graphic that shows the root servers and all of the mirrors. And you can kind of see that they're just labeled by different letters. Okay, let's talk about the web. The web is pretty intuitive to most of us. We have the World Wide Web, which is the www. That pretty much has kind of fallen out in most favor. Most people don't use that anymore. You can almost always omit that from the front of a website address, and either the hosting server will fix it on its end, or your browser will fix it, one of the two. So when you request a web page, I'm going to get into a couple of things here that are important, particularly the concept of the URL. When you actually go out and request a web page, in the example here, http:// some site address / blah, 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 and then a GIF file. Note that there's three parts to this URL. The first part is the protocol, in this case HTTP. It could be other things like FTP. And the second part is the actual computer domain name, which identifies the server that's holding the information. And the last part is the path name. And this part's going to become more important to you as we get into the HTML part in chapter 4, because you're going to have to find out or figure out how you're going to organize your own path names and file names for your web page. So it's a universal structure, and it may not seem like it sometimes because they've gotten where you can be fairly sloppy with your browsers, and if all you put in is to your browser is google.com, it works. That's because the browsers go in and they fix it for you. But when it goes down to the IP layer, it's still got to have all that information in there. What happens when you get it wrong? Well, the system is set up to provide back a 404 error. You've probably seen these. It can mean fundamentally two things. It's broken on the other end, or you can't type. One or the other typically is the way that works. Okay, we're going to get into HTML programming in the next chapter, but we'll just talk real briefly about that here. HTML is a markup language. It's like a code. Technically, it's not code, but it's a markup language. It's given here in an example. We're going to learn all about what those different tags mean. The tags are the bit that's in purple and enclosed by less than and greater signs. One of the things that's used to note is that in the path of a server, when you typically type in a website like, say, google.com, there's an assumption there that there exists a file at that root level of that web server, and the name of the file is typically called index.html. You don't have to type that in because it just automatically assumes that it'll be that or one of a couple of other standard defaults. You'll be creating your own index.html page here in the next chapter. which brings us to the whole file structure scenario, which I believe we'll cover here in another video so that this doesn't get too long. So that will be all for this one.